Good morning. Last class we discussed about the what is meant by gas power cycles and air standard cycles, and why it is necessary to study the air standard cycles. So I just repeat with few words again. An air standard cycle is a reversible cycle, that all processes are reversible. The working fluid is air, and where heat is added from outside source. It's not like that it is generated internally, though heat is not generated, in fact this is the wrong word, but the internal energy is generated inside, which boosts up the temperature of the working fluid. It is not like that. The temperature of the working fluid increases because of a heat addition from the outside source. Why I am telling this? Because in many practical gas power plant, the temperature is generated inside because of the generation of internal energy. So the working fluid gets heated. But when you study an ideal cycle, that is an air standard cycle, we consider heat is coming from inside, outside, and heat is rejected also to an outside sink, source and sink concept. And throughout the cyclic processes, air is the fluid which behaves as an ideal gas with constant specific heat. So today we will first study this one, the Carnot cycle. Today we will first study the Carnot cycle. Carnot cycle. Now Carnot cycle we have also studied in few last occasions. So we know what is a Carnot cycle. Now Carnot cycle, if you plot the PV diagram for Carnot cycles, you will see the Carnot cycle consists of two isotherm and two isentropics. So these are the two isentropics lines. S is constant, and this is T is constant. So this line is constant temperature line, T is constant. So these two lines is T is constant. So it consists of two isothermal and two isentropics. We can start from any point as one, it goes in this direction, and isentropic expansion 2. Where the volume is increased, specific volume, per unit mass. I am drawing the cycle. This we have drawn earlier also in some other occasions. Then there is an isothermal compression, that is 2 to 3 process. Then again 3 to 4 is an isentropic compression, this is isentropic process, and 4 to 1 is isothermal expansion. These three processes are there which constitute the Carnot cycles. If we draw this diagram, first and foremost task is to draw the diagram in PV and TS plane. You will have to develop this habit. Now 1 to 2, 2 to 3, you start with that. 1, 2 is an isentropic process. So an isentropic process obviously will be a line like this. So this is 1, 2, this is 1, 2, this is 1, 2. Similarly 2, 3 is isothermal process. So this will be 2, 3, sorry, this is 2, 3, I am drawing by a black. So this is 2, 3. So this is 2, 3. Again 3, 4 is an isentropic process. This is 3, 4, and 4, 1 is again the isothermal process. Okay, let me stop drawing by different pen. It will take unnecessary time. So therefore we see that the Carnot cycle looks like this in PV and TS diagram. Now, before calculating the cycle efficiency, network output, there are many things which may have to calculate it. Network output, cycle efficiency, what is the output, what is the power output in process 1, 2, what is the gross heat added, many things we can calculate. So best process is to do it that if you make a table like that, process where you write the process, different process, 1, 2, that means this process, 2, 3, there are 4 process, 3, 4, and you go on computing this delta U, change in internal energy of that process, work and heat quantity. One thing is very important in analyzing this type of air standard cycle. Two informations are very important. One information is the working fluid, which is ideal gas. Ideal gas. Which is ideal gas? Air. Air is the working fluid which behaves as an ideal gas. Ideal gas is a broad thing, air is the working fluid. Next important thing which is very much needed is this: what type of process is performed by the gas. That means whether it is a non-flow process or flow process. So, the answer to this is non-flow process. That means process performed in a closed system. These two are extremely important while evaluating the parameters like work done, heat added, all these things. Non-flow process, though change in internal energy is not required, it is a point function because it is difference of the property. As you know, for an ideal gas it is Cv times delta T, but for W and Q it is very much important whether the process is a non-flow or flow process. Accordingly things will change, you will see afterwards, we will study another air standard cycles, Breton cycles, where the processes are flow processes, steady flow process. So it is extremely important to know what type of process it is. A non-flow process being performed by the working fluid air during the cyclic operations. Non-flow process means process, that means process executed by a closed system process. Now you see the process 1, 2, you start from process 1, 2. Okay, 1, 2 is an isentropic process. So what happens? Reversible adiabatic process. First of all, you see whether any of these three columns there is a special case or not, so that I can put 0 or something like that. You have to see first. So for this process, is there any of these three column will be 0? Yes, this one 0. So better you do that first. Now what is the technique? This is the way, if you do it will be very clear, I am telling. Books may not tell that. Then what you do, you write the first law of thermodynamics, which is Q, which is valid for the closed system in this fashion, del U plus W. Now next is that, first you search whether there is 0 for these two columns. Next is the del U. Del U, always shutting your eyes you can just write for any process without seeing any cycle, that if process is 1, 2, then its change is internal energy is T1 minus T2. Where from does it come? It comes from the concept that ideal gas. So this column you can write without seeing even the shape of the cycle. But from the particular process you can write here Q is 0. So when Q is 0, now this equation you see. When Q is 0, work done is minus delta U. Here I am writing only work done. So plus minus sign will indicate whether work is done or work is being done on the process. So W is minus delta U, that means this will be simply Cv T2 minus T1. Cv, oh I am sorry, it will be T2 minus T1, I am sorry, it will be T1 minus T2, T1 minus T2, correct? Now next comes to the process 2, 3. Now one thing is that in this process T1 is equal to T4. One has to write that T1 is equal to T4. Let this is equal to TA. T1 is T4. That means this is TA line, isothermal. Similarly, T2 is equal to T3 is equal to TB. That let this line is TB line. That means there are two isotherms, TA and TB, and two isentropic lines, isentrops. This is the Carnot cycle. Here also this is TA, this is TB. Now next part is 2, 3. You tell me 2, 3, is there any column where I can write 0? Which column? Delta U, the first column, very good. So you have started thermodynamics well. Then if delta U is 0, Q is equal to W. So if any of the two quantities is found, that means we can write for both these. How to find out which one is simple to find? Q. How to find out Q? Tell me. T into delta H. Why T into delta H is Q? Where from you get? You have to find out from the basic. Why Q into delta H is T? Is a reversible process, so what? So how do you, what is the equation which gives you the heat transfer in this process 2, 3 is Q into delta H? How do you know? How do you know? So you have to find out W. W is what? This is a non-flow process. It is PdV. If it is not non-flow process per unit mass, that's why small v. It could not be PdV. In that case, work done is equal to something else. You have to go for the steady flow energy equations. Very careful at this stage. Don't do a blunder at this stage, which you can calculate from equations. PdV is the work done, reversible non-flow process. Only work done is PdV. There is no other work except the displacement mode of work. Alright. Now, if you evaluate PdV, you see that PV is equal to what? RT2. PV is equal to RT2 or RT3, because this is same. PV is equal to R T2 or RT3. That means during this process temperature remains constant to 3, which is TB. That means I can write RTB, T2, T3, TB, RTB, PV RTB by V. That means this will be ln V3 by V2. So this is the work done. Clear? Hello? Okay. So therefore I write RTB, TB ln V3 by V2. So since delta U is 0 from the first law, Q is equal to W, so Q is RTB ln V3 by V2. Clear? Now 3-4. Now here one thing you see before that, this is an isothermal process where volume is reduced, that is a compression process. This was explained physically earlier. So in this process both work and heat transfer is there. Now you see, if you consider this term work done, V3 is less than V2, that means this is negative. That means work is done on the fluid. If you see this term RTB ln V3 by V2, this is also negative, the same term. That means heat is being rejected by the fluid. That means isothermal compression process where heat is being rejected by the fluid and fluid is being compressed. What happens? Just you imagine in a piston cylinder arrangement, this was explained earlier, if there is an air, if you want to compress the air at a constant temperature, what will happen? You want to compress the air, that means you give the work. Okay. So when the temperature is constant for the air, the temperature has to be constant. It behaves as an ideal gas, and moreover it is isothermal process. That means if temperature is constant means the internal energy will remain constant. That means you want to make an isothermal compression. Isothermal means temperature remains same, and temperature remains same means for an ideal gas internal energy remains same. That means when you compress it, the work of compression which is being added to the working fluid has to come out in the form of heat, so that heat has to be rejected so that the temperature remains same. This is the way one can understand. Also one can understand without this heat and work that okay, if I compress it, its temperature will increase. To make the temperature constant, I will have to take heat away so that it is cooled and temperature is maintained constant. So therefore this is a process where heat is being rejected and work is being, heat is being rejected and work is being done. That means this is the process where heat rejection takes place. Let this is QR and work is being done on this process. Work done, W. I am just writing on W. But in this process there is an work, but there is no heat. There is an work, W12. This is W23. This QR is Q23. I am writing as QR because heat is rejected. Heat transfer processes are only 1,4, 4,1 and 2,3 because these two processes are reversible adiabatic process. There will be no heat transfer. So whenever you write these things in the table, you complete one row, different columns you fill, then immediately you physically understand that what. For example, this process there is no heat transfer because it is an adiabatic process. Reversible adiabatic is an isentropic process. There is an work done which is positive, work is coming out, and there is a change in internal energy. Alright. Now I come to the process 3-4. 3-4 is synonymous to 1-2 in respect that this is 0. So what is this? CV T4 minus T3. So what is this? CV T3 minus T4, negative of this because Q0 W is minus delta U. So you see there is T3, T4 is more than T3 or T3 is more than T4. Here you cannot see it here, T4 is more than T3. T4 is more than T3. So therefore you see that there is an increase in internal energy, but there is a negative work. That means work is being W3/4 given to the system. There is no heat transfer. Clear? 4-1 process, again 4-1 process which will be 0. It is the synonymous to this 2-3 process. So that means this is delta U 0. So W is RTA, in this case it will be RTA. ln final volume means V1 divided by V4. Similar is the thing that for the work because delta U is 0, RTA ln V1 minus V4. If you recognize this, you see there is no internal energy change, just the reverse, get an expansion. So heat has to be added because it is expanded means its temperature is reduced. So constant temperature means heat has to be added. And if temperature remains constant, internal energy remains constant. That means the work which is being developed by the expansion has to be nullified by the amount of heat which has to be supplied, so that summation of these two is 0, algebraic summation. There is no change in internal energy. So therefore you see here V1, V4, V1 is more than V4. So therefore this is positive, work is done. So in this case work is done, W41. And the heat quantity, you see similar way, V1 is more than V4, that means this is the quantity, so that heat is being added to this system, QA. So QA is the heat added, which is the isothermal heat addition 4-1, and QB is the heat rejected. That means this is QA, heat is added. This was discussed earlier also in Rankine cycle, the same cycles, QA, and this is the heat rejections, QR. And work quantities are involved in all the 4 processes. In a closed system, work quantity will become 0 only if there is a process with constant volume, dV is 0, isochoric process, constant volume process, otherwise all processes work transfer is there. So I think this is clear. This table, after you complete this table, you check the first law of thermodynamics for a cyclic process. What is that? Delta U, sorry, sigma of delta U has to be 0, and it is 0, you see. T2 is T3 and T1 is T4. T2 is T3 and T1 is T4, so they cancel out, it becomes 0. If you sum it up, 0, because T2 is T3, T1 is T4, T2 is T3, T1 is T4. Now delta W, what is the, if delta U is 0, the cyclic process delta W must be equal to delta Q. Delta W and delta Q are same. If you do that, you see here also T2 is T3, T1 is T4, that means these 2 terms cancels out. So therefore this plus this is equal to this plus this. So therefore the sum of this column is sum of this column. If one can do these things, but he is through, he can calculate anything whatever is asked for. But what is the most important thing that is asked for is thermal efficiency. Now thermal efficiency, it is always better without going for calculating this sigma W until unless it is asked for, what is the net power output of the cycle or work transfer for a particular process, then you will quote this result. So better only if thermal efficiency asked, we should write from this. What is thermal efficiency? Heat 1 minus heat rejected by heat added. That means heat rejected, heat added by heat rejected, heat added minus heat rejected divided by heat added. That means 1 minus heat rejected by heat added, because here heat rejected term is already negative. Which is the heat rejected term? This one. Okay. And what is the 4-1? No, heat added term. I am sorry, heat rejected term is this one, which is already negative. So that I can write 1 plus RTB ln V3 by V2 divided by RTA ln V1 by V4. So with a minus sign I can write eta is 1 minus RR cancels TB by TA into ln V2 by V3, so that make it positive, V2 by V3 by ln V1 by V4. So immediately my common sense dictates that since the efficiency of a Carnot cycle is 1 minus TB by TA, so these 2 things automatically will cancel. How can you cancel V2 by V3 as V1 by V4? You have to write the, now any manipulations you will have to do now with the process calculations. Now for this isentropic expansion process 1, 2, what can we write? We can write this. If we, before writing this, I just tell you that these equations will be very important for isentropic process. PV to the power gamma is equal to constant. That we know for an isentropic process performed by an ideal gas. PV to the power gamma is constant, where gamma is Cp by Cv. This is a very important relation. This will never be given in examination. Now at the same time we know PV is equal to RT. PV and T are related for an ideal gas like that, where R is a constant, characteristic gas constant. This has been told. So if you want to know PT and VT relationship, we will have to substitute one, either P or V, which is not required from this equation here. So if I want to know the VT relationship, P is substituted, that means RT by V into V to the power gamma is constant. Or I can write T by V to the power 1 minus gamma is constant. or one can write V by T to the power 1 by 1 minus gamma is constant. Anyway we can write V by T to the power 1 by 1 minus gamma is constant. So if I use this relation V by T to the power 1 by 1 minus gamma constant, then it will be easier for me, because here I want to relate this V's. That means I can write V1 by V2 is T1 by T2 to the power 1 by 1 minus gamma, 1 by 1 minus gamma. V is directly proportional to T to the power 1 by 1 minus gamma. You will have to work out this. This you do not have to keep in memory. Similarly, I can write for this process V4 by V3 is equal to T4 by T3 to the power 1 by 1 minus gamma. Now T1 is equals to T4, this is an isothermal process. Similarly, T2 equals to T3, this is an isothermal process. That means V1 by V2 is V4 by V3. That means V1 by V2 is V4 by V3, which means that V1 by V4 is equal to V2 by V3. That means which I want to prove that this equals to this. So these two cancels out and I get eta is 1 minus Tb by T, which is the efficiency of a Carnot cycle. That means 1 minus the efficiency of heat rejection, temperature of heat rejection divided by the temperature of heat addition. Okay. Another interesting feature here, that the when you draw the PV diagram, what does this closed area of the closed loop represent? This represents the work done. What is the area of this closed loop represent? Heat, total heat added, net heat added. So the area, these two areas, are they equal? Yes, this is because delta U is 0, and the basic first law of thermodynamics is that algebraic sum of the work is equal to algebraic sum of the heat. That is the conservation of energy, because the system comes to the initial stage where there is no change in the internal energy. So this is okay. This is the Carnot cycle. Now I will come to Otto cycle. What is an Otto cycle? Next is an Otto cycle. It's named by, this was named by Carnot, as we have right, Sadi Carnot and French engineer. Otto cycle is a German, Otto cycle. Otto cycle is another air standard cycle. Otto cycle, air standard cycle. Now I will explain afterwards why a Carnot cycle is not used for any gas power plant. But air standard cycle, Otto cycle, is a theoretical cycle of a gas power plant. Like the Rankine cycle was a theoretical cycle for a steam power plant. Similarly, Otto cycle is followed for an automobile engineering, automotive engines or automobile engines using petrol as the working fuel. That is the petrol engine. We simply call that is a petrol engine, and it is known as reciprocating IC engine. So therefore, without going into any details of reciprocating IC engines, reciprocating spark ignition IC engine, this is the terminology. We just want to see, we like to know that what are the operations that a reciprocating IC engine performs, spark ignition engine performs, so that we can understand the cycle, just like the way we appreciated the different components of a steam power plant and what are the operations. For that reason only, we just go, probably you know this thing from your popular knowledge, that a reciprocating internal combustion engine which work on spark ignition process, this is like this. Let me draw this first, the figure, then I will explain this. This is a cylinder piston arrangement, and a working fluid performs a non-flow process. I just explain this. Let me explain this thing. This performs a reciprocating motion. This is a center line, and this is a connecting rod and crank mechanism. Okay, this. Now there are two extreme positions. Between which it now thing is like this. This is a piston cylinder arrangement connected with two valves. I will explain this afterwards. This is the piston. This is the piston which makes a reciprocating motion within this cylinder. Okay, and this reciprocating motion is being generated by the use of a rotary motion through a crank and connecting rod mechanism. This is a connecting rod. I am not writing everything. This is the crank. So I can write. This the mechanical engineers will read. Connect. This is one of the classical mechanism by which the rotary to reciprocating or reciprocating rotary conversion may be made. Now it reciprocates within the cylinder between two limits. That means the innermost point or innermost plane to which it can go without hitting the head of the cylinder is known as inner dead center position, IDC or TDC, top dead. So top dead center position, the word top is justified when it is a vertical center. It is a vertical engine. That means it is the top one. But IDC goes for both the case horizontal and vertical. That means the inner dead center. These two are known as dead center. Inner dead center or top dead center in case of a vertical configuration. Well, similarly this is ODC, outer dead center or bottom dead center if it is a vertical engine. So this is the bottom dead center. That means between the innermost and the outermost, that IDC and ODC, the piston makes a reciprocating motion. And this length is known as stroke. Not this length, the volume actually. This one movement from one dead center to another dead center is one stroke. So when the piston moves from one top IDC or top dead center, one dead center to other dead center, either in this direction, the piston makes one stroke movement. That is known as stroke. Now what happens, I am telling that when if we start from this, piston is that the piston is continuously moving like this in a continuous operation, and we get the work done from here. Now what happens, I start from one particular position, the piston is at the IDC or top TDC. In that case what happens, this valve is open. This valve is made in such a way that this is opened in this direction. This valve is open and this valve is known as inlet valve. This is made to open by a mechanism known as cam, which is attached to a shaft known as camshaft. So valve is made to open. It takes some time for a complete opening of the valve. So valve starts opening before the piston reaches the top dead center or inner dead center position. That is true. Before it reaches the inner dead center position, valve starts opening. But we consider as if when the piston has reached its inner dead center position, valve is wide open. Okay. Now then what happens when the piston moves down, the gas or air here, if we consider an air standard cycle it will be air, but usually it is a gas in practice, expands, which was at almost at an atmospheric pressure. That we will come back when we will complete the cycle. So an atmospheric pressure gas expands because of the increase in volume due to the descending motion of the piston. What happens, the pressure inside when the piston is descending and come here, so this pressure inside will be less than the atmospheric pressure, because some gases at atmospheric pressure is expanded, so its volume is increased, so pressure is decreased less than the atmosphere. So there is a suction pressure inside the cylinder. So then air, fresh air from outside, this is connected by a pipeline known as intake manifold. This is intake manifold. These are the usual terminologies. So air comes through this intake manifold to this cylinder. This is very simple. The most idealized case I am telling, there are many things, air filter, this, that, which you will be reading in IC engine class. So air comes in. That means when the piston descends down from the IDC, due to the suction created within the cylinder, the air comes in till the piston goes to the outer dead center position. Alright? Okay? So therefore this is the condition where you see the pressure goes below and again mass comes. So pressure is getting really equalized. Try to understand physically. This is very important, that when the piston goes down, the suction is created. Immediately air comes. Piston goes down, suction is created, expansion, and air comes. So air continuously comes as the piston goes down. This is approximated in theory to be a process of induction of air. Is a process of induction of air at constant pressure. That means it is an expansion process from some volume which corresponds to the volume of this. That is when the piston was IDC, to a volume here at constant pressure. Why at constant pressure? Practically it may not be at constant pressure, there will be a change in pressure, because whenever there is a suction, air is coming. That means fall in pressure is being utilized by the addition of the fresh mass. That is why this is being conceived as if a constant pressure expansion, and in theory it is like this 0, 1. In practice it is not like that. In practice the process is like this. Initially the pressure goes down, initially the suction pressure, fall in suction pressure is much more than the induction of the air, in such a way the pressure is not being utilized, and then slowly when the air mass increases inside this, the pressure takes up to the atmospheric pressure, so that it ends up to the atmospheric pressure. But we approximate this in an ideal cycle or a standard cycle as if a constant pressure 0, 1, 0 is the starting point here, that you will understand why I start with 0 not with 1, 0, 1 as the expansion process. So V1 corresponds to the volume of the cylinder, volume of the gas inside the cylinder when the piston is at the outer dead center position. Clear? Now you consider a situation where the valve is closed. It starts closing much before there, but I am not going into these practical things. There are certain time for closing and opening the valves, which are known as valve timing, which is being done to get the maximum possible power needed. That means heat the iron when it is hot type of thing. That means you have to open the valve when valve opening is much more utilized. You have to close the valve when the valve closing is much more utilized from the viewpoint of the operation of the IC engines. That I am not going to describe. In ideal cases, let us consider as soon as the piston reaches here, instantaneously the valve is closed. This valve is closed throughout. So therefore now the two valves is closed. This valve is closed throughout. So far we have discussed these two valves are closed. That means at this position piston has inducted some air. That means the cylinder is full of air whose volume is V1. Now piston when ascends up, what happens? This air is getting compressed. Okay, I am sorry, it is a spark ignition engine. This is not air fuel vapor. I am sorry, extremely sorry. This is not the air. This was diesel engine. Air is being sucked. It sucks an air fuel mixture, which is known as charge. I am sorry, air fuel mixture charge, which means that the mixture of air and fuel vapor which is being inducted to the engine during this descending motion of the piston. So this is one stroke. As I have told, this trouble is known as stroke, known as suction stroke. So before explaining this in this diagram, PV diagram, I first better explain what happens actually in this engine. So now when it reaches here after inducting this charge, the mixture of air and fuel vapor, when it is full of air and fuel vapor, this valve gets closed, and this valve is also closed. Then what happens? Piston goes on ascending, and what happens? The fixed amount of mass, which is the air and mixture of air and fuel vapor known as charge, this is getting compressed, and when the piston comes to this inner dead center position, then some compressed air and fuel vapor mixture is there within this portion of the cylinder, whose pressure and temperature is high. This is because the compression. The piston is insulated during this part, no heat is going out or is not allowed to go out, so that the charge attains some high pressure and temperature because of the compression by the upward movement of the piston or inward movement of the piston, depending upon the cylinder piston configuration. So then what happens? At this pressure and temperature, this charge mixture of air and fuel vapor cannot ignite spontaneously. This stroke length and the design of this cylinder it is designed in such a way that this compression cannot make the temperature as high as required for the spontaneous ignition or burning of fuel vapor with air, even in the absence of any igniter source, even in the absence of any initiation. So therefore an initiation is required by an igniter. This is an igniter. This is an igniter. So which ignites the fuel vapor and air mixture, for which the burning takes place. Now this burning is an exothermic reaction. The fuel is actually an hydrocarbon compound which rapidly reacts with air. It is a rapid exothermic reaction, oxidation reaction, because of which there is a huge pressure and temperature created within this charge. This thing will be made very clear when I will take the reactive thermodynamics afterwards. So this is an exothermic reaction, though loosely many people tell that which generates heat or liberates heat. That is the wrong terminology. which I will make clear afterwards. So exothermic reaction does not mean that liberates heat, because heat, the question of heat does not come here. This is a closed system which is insulated, so that no question of heat is there, because heat is an energy which is in transit because of a temperature difference. So therefore this is a reaction, exothermic reaction, which makes the products of combustion to attain a very high temperature and pressure because of this burning. That means the rapid exothermic oxidation reaction of fuel vapor and air. So therefore a high pressure and temperature is created, which gives a high thermal energy, is a form of internal energy. From the energy conservation point of view, this comes from the chemical energy of the fuel vapor. All these things will be made clear in the subsequent chapter, which I will describe in this chapter, that is the thermodynamics of reactive system. So this high temperature and pressure of the gas pushes the piston downwards. So therefore the third stroke, the second stroke is the compression stroke, third stroke, while the piston goes downward or goes outwards, expanding this high temperature and pressure mass of the products of combustion, this pushes the piston and the piston moves downward. This is known as power stroke. This stroke we get the power. Okay. Then when the piston comes at the bottom dead center position or outer dead center position, then the temperature and pressure both of this charge, which was here after burning, is reduced. Pressure is reduced, the volume is increased, and temperature is reduced because of the expansion and the work done. Then what happens when it is at this position? Immediately this valve opens, and we consider an instantaneous opening in the ideal cycle, but it gradually opens. It starts opening even before the piston reaches this outer dead center position or top dead center position. These details I am not teaching here. So we consider theoretically or ideally as if the valve opens when the piston reaches this ODC, that outer dead center or bottom dead center position. Then what happens? The gases, some gases are expelled through this manifold or to this duct, that means the exhaust duct, which is known as exhaust manifold, to atmosphere. Then what happens? The piston again ascends upward. During this upward movement of piston bodily pushes the remaining charge at relatively high temperature and pressure as compared to the atmospheric temperature and pressure through this port, through this exhaust manifold to the air. So that when piston goes to this portion, the pressure here is almost atmospheric pressure, there is an equalization of pressure. In fact, when the valve is open, immediately some charge is expelled and obviously the pressure equalization takes place, and when the piston gradually moves up, because of the mass going out, what happens? The pressure remains the atmospheric pressure. So almost we can consider this as an atmospheric constant pressure, at atmospheric pressure discharge. So therefore when the piston again comes to this inner dead center position or top dead center position, it comes to its initial condition, that means this volume which is full of charge, that is burned products of combustion. Then again the piston moves downward to start the another cycle. So this way the cycle of events repeat. So therefore you see one cycle composes of 4 strokes, that means 4 movements of the reciprocating motions of the piston from the IDC to ODC. Okay? And then again the piston when starts descending downward, what happens? It inducts the fresh charge, that is air, mixture of air and fuel vapor. Along with that, these products of combustion also is there, which gets expanded, and that causes some other problems which I will not describe here. Now this is the operation which takes place, the primary operations which take place in an petrol engine, in an internal combustion engine working with petrol. This is known as the petrol engine or spark ignition engine. This is because the ignition is initiated by virtue of a spark here. Now how do we simulate in ideal cycle? Ideal cycle, what we consider? We don't consider air and fuel vapor mixture. Okay? Because you see, when you consider air and fuel vapor mixture, you see the first 2 strokes, that is downward and upward stroke, this system is the air and fuel vapor mixture. But after burning, the system constituents change from that of air and fuel vapor to the products of combustion. So the system composition changes for the remaining 2 strokes, that means the power stroke, downward stroke, and the upward stroke or the inward stroke, that is the exhaust stroke. During these strokes, 2 strokes of this cycle, the working fluid is the products of combustion. So therefore these do not truly this does not truly define a thermodynamic cycle. So an ideal thermodynamic cycle defined like this, as if air is being sucked by the piston and it is being sucked during the downward or outward stroke, during which the pressure remains constant, as I explained in the last class. This is because as it goes down, the pressure inside falls below the atmospheric pressure. At the same time the air mass comes in, so these two things equalize the pressure to make it constant at atmospheric pressure, and that is being represented by 0,1 line. But in actual case the process is like this, by dotted line, where initially the pressure goes below the atmospheric pressure, but the latter part of this suction stroke the pressure increases to atmospheric pressure. But we simulate this as a constant pressure induction of air. Then when the air is pushed in the compression stroke from the outer dead to inner dead center position, and when the piston is insulated, the ideal process should be isentropic, because when the piston is insulated no heat is allowed to flow outside because of the rise in temperature due to compression. This is adiabatic, and moreover if we consider the process to be free from any viscous or fluid friction, absence of viscous fluid friction or solid friction, then we consider the process to be isentropic. So therefore this part of the curve represents the isentropic, S is equal to constant. So this is in PV diagram I am drawing the ideal cycle. So this point 2 represents the state when the piston reaches the top dead center position. Then when the burning takes place, this is very important, when the igniter burns this mixture, air and fuel vapor are so thoroughly mixed before it is being admitted to the chamber, which is done in a device known as carburetor, and the fuel which is used is petrol, which is so highly volatile that it is easily made vapor and can be thoroughly mixed with the air, so that the physical contact is very good, and immediately after ignition it releases the heat, which is a very colloquial term. It makes the combustion complete and the pressure and temperature is instantaneously raised. So this type of almost instantaneous combustion which takes place in a petrol engine, which is known as a premixed combustion, where fuel vapor and air is mixed before and thoroughly, and immediately after ignition almost instantaneously the mixture burns. Sometimes colloquially we tell almost instantaneously heat is being generated, but heat is not generated, but it is immediately burned and raises the pressure and temperature. So this process is so instantaneous, we consider this as a constant volume process in ideal cycle, as if with the limitations that during this process of completing the combustion and raising the temperature and pressure of the charge, piston gets a little downward movement. The time for which the downward movement of the piston is very little, so that the process is almost complete within a constant volume. You understand? And moreover, we consider in ideal cycle where there is no fuel vapor mixture, there is air. That means this particular burning, almost instantaneous burning process is simulated as if piston is fixed at the inner dead center position and air is heated from outside source, air is heated to raise that temperature at constant volume. It is clear? So this is the reason for which this burning process in a petrol engine is simulated by an heating process of the air, which is the cyclic fluid, at a constant volume, where heat is being added from outside, QA. This part is clear to everybody? This is the most important part in this cycle. Then obviously the power stroke, which is the descending stroke or outward stroke from IDC or TDC to ODC or BDC, which has to be also an isentropic process. 3-4. Ideal case, this should be an isentropic process, but it is not the isentropic process. This is because the temperature is so high after the burning. If you allow the piston to move downward, temperature decrease is relatively less during this descending motion, so that the piston material, the surface material cannot withstand that temperature. So effective cooling arrangement is made by passing water through water jacket surrounding this cylinder tube surface from outside. This is the actual case. But when ideally we will consider this system should not reject any heat to the outside fluid, so that we can get the maximum power. So it is simulated by an ideal process at S is equal to say an isentropic process. Then what happens, again the important part is here, that when it reaches that 4, similar to this inner dead center position, when it reaches that ODC, that means the state 4, immediately the valve is open. We consider that valve is open instantaneously. So when instantaneously the valve is open, we consider all the all the hot air which was there after the expansion is expelled through this, so that this process is instantaneous and the piston almost remain at the outer dead center position. So this is replaced by the 4-1, and then we consider as if open this instantaneously, some hot mass of air immediately is expelled to make this pressure same to the atmospheric pressure. That means pressure equalization. You make the valve open, this pressure difference causes the air to flow. So immediately the pressure equalization takes place. The air here is at atmospheric pressure, and then the piston moves upward to push the remaining part of the air going out of this exit manifold or outlet manifold. Now this thing happens similar way, is simulated in the similar way of the suction stroke or the induction stroke, that at constant atmospheric pressure. Why? Because when you push this, there is a compression, so pressure should rise, but this is an open system. That means this is open system, means this is going out. So you understand, exactly this is an open system, the mass is going out, so that if we conceive it as a closed system, we can conceive it as a constant pressure exhaust. That means constant pressure discharge of the air. This is because the increase in pressure is being nullified by the exit or efflux of masses, the way the decrease in pressure was nullified by the intake of masses. So that the inlet admission of the air, that is inlet stroke, is taking place in this direction 0 to 1 at atmospheric pressure. Similarly, the exhaust of the air after the point 1, when the piston reaches the outer dead center position or bottom dead center position, is also simulated by the process 1, 0. They cancel each other. So ultimately we are remaining with 1, 2, 3, 4 process that defines a cycle. This is a constant volume, this is a constant volume process. I am not writing, this is the PV diagram. So here you see, here heat is rejected. That means heat is added at constant volume, heat is rejected. That means in actual practice what happens, when the piston descends at this position, we keep a sink here where heat is being rejected. You understand? And this air is coming to point 1. You understand this thing? That means the simulation is like that. First of all, it is air is being taken in, and this is the process 1, 2, the air is taken in here. So when we simulate the ideal cycle, we just remove this air induction part and the discharge of air part, because they two cancel each other. So now you think in this way, there is a cycle which starts like this, there is some amount of air in a closed system. Now is a closed system cycle, which is first isentropically compressed, then after isentropic compression to a volume 2, that means here I do this way 1, 2, 2, then at this point, keeping the piston fixed at this point, we bring a source and heat it to a temperature 3. You understand? Then from 3, we allow the piston to come down or come out, so that an isentropic expansion is there. When it comes, this is 3, 2 to 3 is the heating. Then when it comes to 4, then what we do, we keep, then we remove the insulation, we keep a heat sink and make an instantaneous heat rejection process at constant volume. Or it may not be instantaneous, it may be a heat rejection process which is made at constant volume, because then reversible heat rejection or reversible heat addition will not be instantaneous, it will take time, but in actual case it is instantaneous, so that we can simulate it at a constant volume. But when we will explain it with respect to an ideal system with air as the working fluid, we will make that heat sink is there with which heat is being rejected, making the volume constant. So 4 to 1. So therefore 1, 2, 3, 4 is an ideal cycle. If you have got any query, you tell me, and this cycle is known as Otto cycle. So Otto cycle is this 1, 2, 3, 4. So I could have started like this. There is another way of starting. Let us read the Otto cycle or analyze the Otto cycle, which comprises of these 4 processes. 1, 2, isentropic compression in this direction. 2, 3, a constant volume heat addition where the pressure and temperature is increased, and 3, 4 is an isentropic expansion, and 4, 1 is a constant volume heat rejection, and the working fluid is air. So this way I could have started the definition of Otto cycle, but I tell you that this Otto cycle is a representation, theoretical representation or a theoretical cycle of an actual spark ignition or petrol engine. Clear? This thing, how do you conceive this Otto cycle from the actual operation of the spark ignition engine? So rest part is now a routine part. Now I again draw the PV diagram of the Otto cycle before going to do our routine job. So this is like this. So doing our routine job. So this is 1, 2, 2, 3, 3, 4. So this is S is equal to constant, this is S is equal to constant, and we see that heat transfer takes place only in these two processes. That means in this process heat is added QA, a small a also dq, and this process QR, heat is rejected. Okay. So now we can draw the TS diagram also, because this practice you have to develop in TS diagram. In TS diagram what we do, 1, 2 is the isentropic process which is like this, 1, 2, then 2 to 3 is the constant volume process which looks like this in the TS diagram, then 3 to 4 is again an isentropic process, and 4 to 1 is the constant volume process. So therefore this is constant volume, this is constant volume, these are isentropic process. So therefore heat addition is there only in two processes, this process heat added and this process heat rejected. So therefore the area under 2, 3, this area 2, 3 AB is the heat added and 1, 4 AB is the heat rejected. These are all well known things, so that we can represent the this cycle in PVTS diagram. Here HS diagram is not necessary, because the ideal gas, air is an ideal gas as the working fluid, so enthalpy is nothing but Cp into T. So therefore TS diagram is enough, because there is no difference between enthalpy and temperature, it is only a function of temperature like Cp into T, directly proportional to T. So therefore enthalpy entropy diagram is not required. Now you go one by one, 1, 2, this is S is equal to constant, 1, 2, this is the diagram. Okay. Now you tell me one by one, during 1, 2 process, that means the isentropic compression, is any one 0? Which column? Which column is 0? Third column. Then what is that now? This is a closed system. So again this thing is that closed system, that is non-flow process, that is non-flow process, that is non-flow process. This is very important. And air as the ideal gas, non-flow process, non-flow process. Then we have to write the corresponding first law of thermodynamics, that Q is equal to delta U plus W. Bas, that's all. Then delta U, when Q is 0, W is minus delta U. So we have to find out delta U. Delta U I have told always you write for any process 1, 2. It is CV T2 minus T1. There is no doubt, so long it is an ideal gas, the change in internal energy is CV T2 minus T1. Then what is work done? So work done is minus delta U. So work done is CV T1 minus T2. Well, CV T1 minus T2. So T1 is greater than T2. So T1 is less than T2. Sorry, I am sorry. It is T2. Yes, T1 is less than T2. So work is done. This is negative. Work is done on this system. Then for constant volume process, can you tell anything is 0 in this column? W0. W0. So when W is 0, Q is delta U. So delta U is same. What is delta U? CV T3 minus T2. And you see T3 minus T2, T3 is more than T2. That means there is an increase in internal energy. And since W is 0, Q is delta U. So Q is CV T3, and that is positive. That means heat is added in during this process. 3, 4 is synonymous to 1, 2. This is 0. And this will be CV T4 minus T3, final minus initial, and therefore work done is CV T3 minus T4. Clear? And here you see T3 is less than T4, T3 is more than T4, I am sorry, T3 is more than T4. So therefore this is positive, that means work is done in this case. That means work is done in this case, work is done on this system. The work is done by the system, and there is a change in internal energy, which is a decrease, because T4 is less than T3. The internal energy is decreased. Clear? 4, 1 is synonymous to process 2, 3, constant volume. Why W is 0? PdV. I am sorry, work done is 0. Very good. PdV. Work done is 0. So then what is CV? This is always T1 minus T4. This is very simple, a child can do, that is the final minus initial. So this is the process in this direction, CV T1. So heat added is equal to delta U. That means CV, same thing, T1 minus T4. So T1 is less than T4, this is negative, so heat is added to this system. So if you can make this chart, everything will be clear. So you prove this, delta U 0 and delta W is equal to delta Q. So then this part is clear. Next part, we will find out the efficiency of this cycle. So efficiency of this cycle can be defined as 1 plus, why I am writing plus, because I am using this value. So what is heat added? Heat is added during this and heat is rejected during this, CV. So this is already negative, CV T1 minus T4 divided by CV T3 minus T2, or I can write 1 minus T4 minus T1 divided by T3 minus T2. T4 minus T1, if I do that, then this is a positive quantity and represents the heat rejection. That is why I am writing with a minus sign now. So 1 minus heat rejected by heat added. So heat rejected is taken in its sign, algebraic sign. That is why I have written here plus. Or one can tell that CV T4 minus T1 is the heat rejected, that is the amount of heat rejected. So it is clear now. Now we will have to derive this expression in terms of one important parameter, which is known as the compression ratio. I think time is up for today, which I will do for the next class. From here I will derive this expression eta. So we will have to make a process calculation to express in terms of the compression ratio. Do you have any question? Please ask, because please.
Why don't we consider air plus fuel mixture?
Why do you not consider?
In the ideal condition, why don't we consider the fluid, the cycle fluid as air plus fuel mixture?
So I told you, because this is an air standard cycle. So here we consider air as an ideal gas. If we consider the air fuel mixture, I cannot consider the air fuel mixture throughout the cycle. So its constituents changes, it does not define the cycle definition. So when you come back, even if your pressure and temperature remains the same, but if you start from this point, you come back, but your constituent elements are changed. So you have to do with only one single fluid. And air standard cycle does that with a single fluid, air as an ideal gas. Okay? So that is the reason. Any question? So next please.
So in case of the carbureted engines, the air and fuel mixture are mixed, so it can be considered as an instantaneous combustion. But in the modern fuel injected engines, how is it modeled?
How it is modeled? This is beyond the scope of this thermodynamics class. First thing is, this modeling is not done in thermodynamics. We are studying the air standard cycles only. How the air mixture is modeled, but how the air mixture is made in the carburetor, that is a different story. You have to understand that in a petrol engine, the air and fuel vapor are mixed before the engine and then it is being directed to the engine cylinder. So this is the practice. But I am not going into any detail of this modeling. Now we are simulating this cycle with an air standard cycle, Otto cycle, where air is the working fluid. There is no air fuel vapor mixture, nothing, and air is being heated from outside. The heat is being rejected with heat transfer to the outside. That is the air standard cycle. Okay? All right?